This video is going to cover superposition for slope and deflection. I absolutely love superposition. It is my favorite topic in all of solids, and we've actually been using it before in other topics that we've done. And superposition is when you break a problem into a lot of smaller components and then add them together at the end. So when we were doing biaxial bending, and we broke it into bending in the X and bending in the Y, and then added them together, that was superposition. When we did combined loads and we had axial stress and bending stress and we added them together, that was superposition. Same thing with our shear stresses, torsional shear stresses and transverse shear stresses, and we added them together, that's superposition. So the same thing is going to happen here for slope and deflection by using Appendix C. So Appendix C looks like this. It actually has 2 pages to it. The first page is for simply supported, and the second page is for a cantilever. So how it's going to work is you have obviously more than maybe one case of loading, or your loading looks a little fun, perhaps not very enjoyable when you do it in terms of moment equations in terms of X. So, but this one, you can break it up into its different little parts and then read what you need to, either the maximum slope, the maximum deflection, or using the elastic curve equation, the deflection at a different point. And of course, we have our different loading cases for cantilevers as well. So all of these are really fun. You just kind of have to pay attention to what they're doing. Like deflection max is at the middle on this one, whereas for this guy, they actually will tell you an equation for where something is. If it's not at the middle or something obvious, then they'll tell you exactly where X is. It doesn't mean it's a pretty number, but they'll tell you. If your slopes are different, they'll actually label theta 1s and theta 2s. Now, what you might be noticing in here is all of the positives and negatives. So it's a really good thing to start off by talking about our sign convention. So remember that for bending here, we had our elastic curve. We said that going counterclockwise is positive. Okay, when we're measuring X from the left. And we also said that deflection was positive as well when measuring from the left. Now, deflection being positive going up, that was kind of consistent. It didn't matter either direction. So hence, you're going to notice every single one of these deflection equations has a negative, because every single time the elastic curve is going down, going down, going down, and again going down. So it doesn't matter. It's always how we're labeling it. It's going to be down for all of our examples here. However, if you had your load going the opposite direction, so instead of having your uniformly down load, if you instead had it uniformly up, well, then obviously your elastic curve would be bending the other way. So in which case you would have to turn that into a positive instead of a negative. So when you're reading off of the chart, you got to pay attention to what directions things are going. If your stuff is going in the same direction as theirs, great, use their signs. If your stuff is not going in the same direction, then we have to return to our sign convention. And we're going to kind of see that throughout this example. On times when you have the same kind of picture, like that is our picture, however, maybe our loading is on the other side. So instead of having moment over here, we have moment on this side. Technically, if I'm looking for slope at this point, slope is now at that point, which is actually theta 2, right? So I am actually, in this case, looking for theta 2. However, because I'm flipping my picture around, I need to flip my sign around. Okay, so if I flip my picture for slope, I need to flip my sign. If I flip the direction of my load, I need to flip my sign. So it can get fun, but if you can be creative with it, then all of this gets actually enjoyable. But if you're not creative, then this kind of sucks. So let's see an example. In this example, we have 3 different loads. So that's probably the world's nastiest equations in terms of x. And we have a 15 kip-foot point moment at A on our simply supported beam with a grand total length of 10 feet. We have a uniformly distributed load of 5 kips per linear foot across the whole beam. C is right at the center, and we have 8 kip vertical force right at C. What we want to do is find the slope and find the deflection at C. Now, technically, we've actually used this symbol for deflection, and recently we've been using V for deflection. I'm going to stick with using V for deflection. But in case you happen to see it as lowercase del, that is effectively still the same thing. So slope at A, deflection at C at our little midpoint. So again, we're going to break this up into our different loading cases. So I'm going to start with my red case here. So again, I have a simply supported beam, and I have my point moment of 15 kip feet on this beam. It is 5 feet from each side to the center point C, and that's where I want to find deflection. So first things first, I need to find slope at A. So again, we're going to go over to our picture here. We're going to find the point moment. That's this guy right here. However, my moment's on the other side, so I need to, in my brain, flip the picture. I'm still, however, looking for the slope on the side of my moment. So I am using theta 2. However, I'm going to flip the picture, so I need to give it a negative. And then technically, I'm going the opposite direction. Right? In this case, this moment in our appendix here is ultimately pressing down from above. But in my case over here, I'm actually pressing up from below. So I'm going the wrong direction. So I'm going to have to add yet another negative to my equation. So ultimately, for my theta A, I'm actually looking at a negative theta 2 equation. So that's going to be positive ultimately, which is m naught times L over 3 EI. So m naught times L over 3 EI. I can plug in my values now. M is 15 kip feet. My length is a grand total of 10 feet. And I'm dividing by 3 EI. So my slope A is going to be positive 50 divided by EI in kip feet squared. Cool. So now I need to find deflection at C. So deflection at C is going to be the middle. So we'll kind of clean up our picture again. So I'm looking for right in the center. And that's definitely not right in the center, so I'm not using that equation. So I do have to use this equation. But again, because my load is actually trying to pop this dude up, my elastic curve is this way. So I'm actually going to have a negative of theirs, which is ultimately going to make mine positive. However, what is x? Technically for us, we're at the center of 5 feet, so obviously x is 5. But when you're looking at these equations, you have to look at where we're measuring x from. And it's always from this left point over here. So if you notice, we have the vertical axis of deflection and the horizontal axis of x, and they intersect over at that left point in every single picture. So when you see x, the distance of x here in all of these equations, that is always measured from this left side. Okay, but for our case, it's really nice and wonderful because it's 5 feet, and 5 feet is the same in both directions. So going through, we have minus a minus. We're going to have positive m naught times x divided by 6 EI times L times L squared minus X squared. So, okay, that's fun. Let's plug in some numbers. We have 15 kip feet times X, which is 5 feet, divided by 6 times E times I times L. L is 10 feet, times L, who is 10 feet, but squared, minus X, who is 5 feet, and squared. So what I get for deflection at A, it's a positive value, meaning it's going up, and that's 93.75 over EI in terms of kip feet cubed. So cool, so I did my first one. Now we can go look at a different load. So let's move on to our green one. So for our green one, we have a simply supported beam, and we have our uniformly distributed load, and that uniformly distributed load is 5 kips per linear foot. Again, point C is at the dead center, which is 5 feet from each side. And we want to find slope at A, would kind of help to actually label A, wouldn't it? And deflection at C. So for my green dude, slope at A, well, he looks exactly like this example. So that's wonderful. So we want slope at A. Hey, that's theta max. So here he is negative because, again, our sign convention. So we're going to have negative WL cubed over 24 EI. It's negative WL cubed over 24 EI. Plugging in some numbers, we have 5 for W, so minus 5 kips per linear foot. We have L, who is again 10 feet. Don't forget to cube him, divided by 24 EI. So my slope at A that I'm going to get is minus 208.3 divided by EI in kip feet squared. Okay, and now I'm looking for deflection at C. So deflection at C for this dude, we have, actually it's at V max. Again, you might be thinking, I can't really tell where it's at. Usually if it's at L divided by 2, they're going to literally draw it in there because they're thinking, yeah, you can tell that that's obviously at the center. So they feel they don't need to say it. If it's not at the center, like for instance, this case down here, you want L over 2, so it gives it to you here, but they'll tell you that V max is at a different X. Right, so but that's not our case. Our case is this one, and V max is at L over 2. So minus 5 WL to the 4th divided by 384 EI. So we said minus 5 WL to the 4th over 384 EI. So plugging that in, minus 5 times W, which is 5 kips per linear foot, times L, who is 10 feet, raised to the 4th divided by 384 EI. And what we get for our deflection is minus 651.0 over EI, and this is in kip feet cubed. And lastly, we have a point load going up at the center. So we have, again, a simply supported beam, and we have a point load going up. I don't have to draw it underneath, actually. I could draw it on top going up. He was 8 kips. And that again is at point C. Point C is 5 feet on each side. So this time, if I want to find slope at A, let's go check out which situation we have. This time, we have it at the center, who is this guy right here. So again, slope at A, they're saying, hey, over here at the end, we're at theta max. So theta max is minus PL squared over 16 EI. However, because our load is actually going up instead, we need to flip the sign. So we're going to have a negative PL squared over 16EI. So we're going to be positive. So again, our theta A is a minus their theta max. And so we get a positive PL squared over 16EI. So we get, plugging our stuff in, we have 8 times L, which is 10 feet, that we're going to square, divided by 16EI. And for theta A, we do get a positive, still 50, kind of funny enough, over EI. Kip feet squared. And for deflection at C, again, because we're popping up, this is actually going to be in the positive direction, right? So our elastic curve is actually going to go this way. So our deflection here is going to be positive, not negative. And of course it is Vmax. So ours, if we were to write it down, it would be negative their Vmax, who is going to be positive for us. And it's PL cubed over 48EI. So PL cubed over 48EI. So P for us is 8 kips. L is 10 feet cubed over 48EI. So what we get for that number is a positive 166.7 divided by EI in kip feet cubed. So now what do? Well, if I actually want to find slope at A, we're all the way here at the end, we're going to add together our red one, slope at A, plus our green one, slope at A, plus our purple one, slope at A, and that's going to give us our ultimate result. So our red one, what did we have? Up here we had positive 50. So our red one is a positive 50 divided by EI. Then our green one, where we have minus 208.3. So minus 208.3 over EI. And then plus our purple one, who is also positive 50 over EI. So in total, we're going to get a negative 108.3 over EI. And again, this is in kip feet squared. So what does the negative mean? Going back to our sign convention, we're taking x from the left on our elastic curve. Positive meant we were going in our counterclockwise direction. So that means if we get a negative, then negative down here is going in the clockwise direction. So that just means that we're really going clockwise. That's all, in case somebody asks. And for deflection at C, we're going to do the same thing. We have deflection at C in the red value, plus we have deflection at C in the green value, plus we have deflection at C in the purple value. So for our red one, we'll do a different color here. We have this 93.75 positive. So for our red dude, we said positive 93.75 over EI plus our green one. And our green one here we had minus 651.0. So minus 651.0 over EI. Plus lastly our purple one, and our purple one 166.7. So a positive 166.7 over EI. And we sum those all together. And again, we do have some different signs. And we're going to get ultimately a negative 390.6 over EI. And of course, this is in kip feet cubed. What does this mean? The negative, of course, does mean that it is going down. So negative still means downward. Because it actually didn't matter from which direction we took x. We always said that positive is going up and negative is going down. So in case somebody asks, that's our official answers. Of course, in terms of kip feet squared and kip feet cubed, divided by EI. So if you actually had values of EI, you could plug those in. So as you can see, superposition makes this really, really, really simple. The only thing you have to watch out for is how you flip the pictures and adjust the pictures based on your arrows, direction of your arrows, and sides that you're doing. So again, superposition is absolutely fantastic, and it makes any complex problem into something that's actually pretty simple.